Morning, folks. Welcome. Give another few minutes. If you've anything you want to ask in the chat before we get started, then please do. So today we're going to finish question 3. We kind of made a start yesterday just on the parameterization of the paths, the line segment, the circle. We'll finish that off today. We'll look at 5 and 6 as well from 2022. Explain the differentiation and squaring. Middle term. I'm happy. I assume that's just is it the unit tangent vector thing? That the question you're talking about? Differentiation and squaring of the middle term. So unit tangent vector. So there would be some differentiation, and I'm assuming that's the question you're talking about. I can't do it out in my head that quickly, I'm afraid, but differentiation and squaring of the middle term. So it's a chain rule to differentiate it. So sure, if that's the question. Can you just confirm that that's the question? Avoid 2 minutes. But what I will do, Helen, if that's the right question, is no matter what happens, I'll do out that full question at the end. Even if it goes over, I'm happy to go over with it. But if you could just confirm that it's that unit tangent vector question, I'm happy to do it at the end. I'll do the full question, I think, just to be on the safe side. Square minus 1. Yeah, that's the middle. Yeah. Well, if it's just that middle term. Okay, so see, do I have a spare slide here? Might squeeze it in there. So it was that 1b. It's just the middle term, is it? You're happy enough with the other, all the other terms are just kind of standard derivatives, right? So differentiation.
Oh, yeah.
It's just that middle term, is it?
Just the middle term. Yeah, I'm okay with normal differentiation, but I'm confused with E, Richard.
Grand. No worries. So that's the term. So you have to differentiate that. Now, if you look in the differentiation tables, you have e to the x goes to e to the x, right? Now, the thing about these differentiation tables is what you'll notice if you look down that page 24 or 25, whatever it is, they're all just 1x. It's cos of 1x, sine of 1x, e to the 1x. I think there's an e to the ax as well for some reason, but I don't know why that's in there. But they're all just 1x the whole way down. If what we'd say is the inner part, like cos of 1x, if that goes to, for example, I'll do a cos example first.
Right.
Like cos differentiates to minus sine of 1x. However, if it goes outside of 1x, if it goes to the likes of cos of 2x, it requires what's called the chain rule. So the chain rule says, and this is not a very mathematical way to say it, but you differentiate as you would expect from the tables, but we also need to multiply by the derivative of what's different to the tables. So if it's 1x in the tables and this is 2x, I need to multiply by the derivative of that 2x, which is 2. So that will be the derivative of cos of 2x. Likewise, the likes of this would require the chain rule. It's not just e to the 1t. It doesn't have to be x, like it could be 1t. So to differentiate that, I'll do what I expect to do from the tables. E doesn't change. So I'd expect to get this. But because it's not just e to the 1t, I have to multiply by the derivative of what's different. So t squared differentiates to 2t, minus 1 differentiates to 0. So that will be the derivative of e to the t squared minus 1. All right? So if it deviates from these 1x's that the maths tables, or the whatever they're called, the table and formula book, if it goes away from 1x or 1s or 1t or 1 whatever, you need to use the chain rule. I'll take it an extra step further.
Right, yeah, that completely threw me in the exam. Well, no, I mean, I hadn't the knowledge anyway.
That's fair enough. That's fair enough. We take it an extra step further. Let's say it was t times e to the t squared minus 1. First and foremost about the likes of this, if you're just joining in, by the way, we're just looking at some differentiation related to question 1b in the 2022 exam. Before we go into chain rule, like I can see that will require chain rule, but overall this would be a product rule problem because I have two functions in t multiplied together. Does that make sense?
Yeah.
So more broadly, before I start looking at chain rule, I'm going to say, well, this requires product rule first. The product rule says u dv dx, here it'll be dv dt, plus v du dt. So, and this is not required for question 1b, but just if it did arise that you'd have to use the product rule for it. So u is t. The derivative of v, to differentiate that, I need the chain rule because it's not just e to the 1t. So I would say it's, well, e in the tables, I get back the same thing. But because it's not just 1t, I need to multiply by the derivative of the inner function, the inner bit, which is 2t minus 0. So 2t plus v is as itself, whoops, then it's freezing slightly, times du dt, differentiate t with respect to t, you just get 1. So overall, I'd have 2t squared e to the t squared minus 1 plus e to the t squared minus 1. All right? If you want to like come back and we'll just do that 1b at the very end if you want. There's no panic.
And the other little bit was the squaring. In the actual answer, I got all confused with the squaring of it. Then I was at a loss starting.
Okay. So
just that term.
Yeah. 2 secs. I'll just try to find something blank somewhere. Look, I'll get rid of the product.
Probably gone into I'm gone into the others. The time the other people.
There's no panic. I'm sure if one person wants to ask a question, usually other people do as well. So there's no hassle. So if we are working out the magnitude, look, I'll write out the full thing. So r of t in that question was, this is freezing slightly, which isn't a good sign, is t cubed e to the t squared minus 1, e to the t squared minus 1, and 3t plus 5. So that was r of t. We were asked for the unit tangent vector to that. And the unit tangent vector formula is r dash t, excuse me, over the magnitude of r dash t. That's our formula for the unit tangent vector. Now, r dash t is the derivative of r of t. So differentiate t cubed, you get 3t squared. Differentiate e to the t squared minus 1. Just did it up there using the chain rule. 2t e to the t squared minus 1. And differentiate the last term, you just get 3. But we do need the magnitude of r dash t as well. So the magnitude of r dash t, the magnitude of a vector is the square root of all of the components to be squared and added up. So 3t squared to be squared
90.
Plus, 90 to the 4 exactly, plus 2t e to the t squared minus 1 to be squared plus 3 to be squared. So this will give us our magnitude once we work that down. So the square root. 3 to be squared is 9. T squared to be squared is t to the 4 plus 2 to be squared is 4. T to be squared is t squared. Now, e to the t squared minus 1 to be squared. There is a rule of indices that says if you have I think this is in the log page or the index page or something in the tables. If you've, sorry, this is freezing and it's kind of catching my writing. If you've a power raised to another power, you multiply the two powers. So here I have e to the t squared minus 1 as a power, and it's been raised to another power. So I'm going to need to multiply the two powers. So I have e t squared times 2 is 2t squared. Minus 1 times 2 is minus 2. And then likewise, plus 3 squared is just plus 9.
Thanks
so that
very
will be
much.
squaring out the terms. All right,
Thanks
no worries.
very much. That's sorted. Yeah. Thank you, Richard.
Is that clear, yeah? You have any
Yeah.
more questions on it?
No,
Yeah,
that's
okay.
fine. That was the bit that really threw me.
Perfect. Good stuff.
Thank you. Thank you.
No worries. Okay, so we started yesterday on question 3, and we parameterized the two parts of the path. So we had a line segment. We covered that already in the 2021 paper. We had a line segment, so we wrote that in vector form and gave the start and end points of it, the t values for the start and end points of it. Then we had the second part of the path, which was a circle. So we parameterized the circle, know that for it. And we found the t values for the start and end points of that. A bit tricky. Maybe the likes of that has been forgotten. But both of these had to be satisfied. This and this equation had to be satisfied. They were simultaneous equations. So we solve it down. Cos is like your x coordinate, sine is like your y coordinate. In polar coordinates, that's what they would be. So for cos inverse of 0, if you calculate that on a calculator, it'll tell you it's pi over 2. It's literally saying the x value is 0. Like, let's say if I just plot a coordinate 0, 1, like the x value is always 0 when it's at pi over 2. No matter how far I go up on the y-axis, the x value will always be 0. But the inverse sine of minus 1 would turn out to be minus pi over 2. And you're getting two different looking answers. But pi over 2 was the x one we would have gotten back, the cos one. But cos is also 0 at minus pi over 2. Because let's say a coordinate of 0 minus 1. X will always be 0 down there as well. So this is the one that satisfies both of the original equations. That was a bit tricky, I think. But we got our t values out of that. The other one solved out, square enough because they were both positive. So t was between minus pi over 2 and plus pi over 3. So that's as far as we got with it yesterday. Now we need to work out the line integral. And what I was saying yesterday was it'll be made up of the line integral on C1, which was our line segment. So we will do that one, plus the line integral along the circle, which was the other one. So we'll do them both separately, and then we just add the two answers together. All right. So we're going to work out the line integral along C1 first. Now, there will be some integration in this particular question. There'll be an integration of cos squared. I've just put two links there to revision videos on integrating cos and sine, which are raised to powers. All right, if you need that revision, those links will be there in the slides afterwards. Okay, but so we're going to work out the line integral along C1, and it was yeah, that's our letter that you're using. And we have our formula for that. So it's our start and end points, or start and end t values, I should say. We'll have to change that function to a function of t, just like we did in the 2021 paper. Now C1, I'll just say R1 would be our first parameterization. So we've parameterized that, and it was, so this is the line segment I'm talking about. It was R1 of t equals this here. So I'll just take that down separately. R1 of t is 1 minus t minus 3 minus 3t and the last one was minus 2 plus t, and it was t between 0 and 1. So for our formula here, a and b are the start and end t values, so they will be 0 and 1. I need to transform my function into a function of t. So the function was given in the question, or the scalar field was given in the question. So I'll write that down. It was x squared plus 2y minus z. It was a plus 2y, wasn't it? Yeah. Okay, so to transform that into a function of t, I'm going to replace x with whatever the x is, 1 minus t, y with minus 3 minus 3t, and z with minus 2 plus t. So I'm going to sub them in. So it's x squared, so 1 minus t to be squared, plus 2 times y is 2 times minus 3 minus 3t, and minus z is minus times minus 2 plus t. Use your brackets and simplify it down. So square out the first bracket, multiplying by 2, 2 by minus 3, 2 by minus 3t, and minus times minus is plus, minus times plus is minus. If you want to multiply that bracket by itself, do that, all right? But if you know the quicker way, that's fine as well. So we have a t squared term. I have minus 2t minus 6t is minus 8t, minus another t is minus 9t. And then I have 1 minus 6 is minus 5, minus 5 plus 2 is minus 3. So there's my function in terms of t for the formula. Let's go plugging stuff in. Are we nearly ready to go? Not really. So I have to differentiate R1 of t and then find the magnitude of that. So just work that out over on the right hand side. So I need to differentiate R1. I'm just calling them R1 and R2 so I can tell the difference between the line segment and the circle. That's all. So the circle parameterization I'll call R2 of t. So I need to differentiate this. Differentiate 1, you get 0. Differentiate minus t, you get minus 1. Differentiate minus 3, you get 0. Differentiate minus 3t, you get minus 3. Differentiate minus 2, you get 0. Differentiate plus 1t, you get plus 1. And for my formula, I need the magnitude of that. So it's going to be the square root of all the components to be squared and added up. If you use a calculator for this stuff, make sure to put the negative numbers in brackets, because a calculator will read it as minus times 3 squared otherwise, and it'll give you minus 9. Just be careful around that. Minus 1 to be squared is 1, minus 3 to be squared is 9, and 1 to be squared is 1. So I get the square root of 11. So that's all the information I need for my formula. Now we're going to substitute in the values and work out our line integral. We have, I'll go to a new slide altogether. So we have the integral from A to B. They were our start and end, I'll just say C1. They were our start and end t values. We have the function in terms of t, which is down here, t squared minus 9t minus 3. Times the magnitude of the derivative of our line segment parameterization, which was root 11, dt. Now, with integration, like if you're integrating 3x with respect to x, you're allowed to take any constant multiples out. Hopefully that rings a bell. So here, this multiple of square root of 11, I'm just going to take that outside. I can multiply it in at the end. Just looks a bit messy there. So we're at 1. And I have t squared minus 9t minus 3 with respect to t. So they're all just standard integrals. I'll add 1 to the power and divide by the new power. T squared will give me t cubed over 3. Add 1 to the power, divide by the new power, and a constant will just integrate to minus 3t between 1 and 0. I have limits, so I go upper limit minus lower limit. The root 11 I'm just leaving. So 1 cubed over 3, so this is my upper limit going in, minus 9 times 1 squared over 2, minus 9 over 2, minus 3 times 1 is minus 3, minus our lower limit. When you plug in 0 into each of those terms, they'll each just go to 0. So we can forget about that one. So in total, I have a third minus 9 over 2 minus 3 is, I'll just open the solutions, not confident, minus 43 over 6. So I'll have minus 43 over 6 times the square root of 11, which is minus 43 over 6 times root 11. All right. So approximately minus 23.77. So that would be the first line integral, so along the line segment. Now we're going to have to look at along the circle. So we set up the same kind of idea. It'll be our same formula between A and B. We'll have the function in terms of t. And this time I'll have the magnitude of R2, the other one. Was our circle parameterization. So let's go back and take down what R2 was. So here was the circle parameterization, 6 cos 6 sine minus 1. And the t values for that were between minus pi over 2 and pi over 3. I am going to double check that. Okay. So again, minus pi over 2 will be our A value, our lower limit. Pi over 3 will be our upper limit. I do have to transform the function into a function in t. So I'll take down the function again. It was x squared plus 2y minus z. So the function in x, y, and z was x squared plus 2y minus z. And I need to substitute in my terms. So x this time is 6 cos of t. y is 6 sine of t, and z is minus 1. So I'll substitute them in to transform it into a function of t. So x squared will be 6 cos of t to be squared, plus 2 times y is 2 times 6 sine of t, minus z is minus times minus 1, which is plus 1. Now we'll square out and tidy up whatever we can. 6 squared is 36. Cos of t to be squared is cos squared of t. 2 times 6 is 12. 12 sine of t plus 1. So that's my function in terms of t. I then need the derivative of R2, and I need the magnitude of that. So again, I'll work that out over here on the right-hand side. So I'll work out its derivative, just differentiate each term. Cos differentiates to minus sine. Now again, going back to what I said at the start, it's just cos of 1t, so I can read it directly from the tables. It's not cos of 2t or 3t or whatever the case may be. So cos differentiates to minus sine, so I'll have minus 6 sine of t. Sine differentiates to cos, so 6 cos of t. Cos of t. And minus 1 differentiates to 0. Not minus 1, sorry about that. So minus z, I'll just get rid of this a sec. So minus z, when I'm filling it in, the z value is minus 1. So when I'm filling it in for z, it'll be minus times the z value, because it's minus z in the question. All right, and then the z value going in is a negative. So minus by minus would give the plus. All right, yeah, no worries, you're welcome. So that's our derivative of R2. And now I want the magnitude of that. Magnitude is the square root. Don't be concerned because there's sines and cos's and stuff, if at all possible. It's the square root of all the terms to be squared and added together. No, 0 squared is just 0, so we'll be able to forget about that one, right? But to square up the other terms, I mean, all you can do for sine squared and cos squared is write them as sine squared and cos squared. So we have the square root of minus 6 to be squared is minus 6 times minus 6, which is plus 36. Sine of t to be squared is sine squared of t. Squared of t. Plus 6 to be squared is 36. Cos of t to be squared is cos squared of t. Now, we have a common factor there of 36 that I can take out. I'll be left with sine squared of t plus cos squared of t. And there's an identity in the tables for that. On the trigonometry page, is it page 14? I think the nib on this has gone too low. It's not allowing me to write. It says sine squared of a plus cos squared of a is 1. I think it's actually written as cos squared of a plus sine squared of a in the tables. But I mean, if you're adding cos squared and sine squared of exactly the same argument, it equals 1. So sine squared of t plus cos squared of t is 1. So I have root times 36 times 1 is 36. The square root of 36 is 6. So that's our derivative of R2 and then the magnitude of that. Okay? So I have all the bits of information now. I have my limits of minus pi over 2 and pi over 3. I have my function in terms of t, which is down here. And I have my magnitude of the derivative. So let's go plugging stuff in. Lower limit was minus pi over 2, up as far as pi over 3. Function in terms of t was 36 cos squared of t plus 12 sine of t plus 1. The magnitude of the derivative was 6 dt. Now, again, I have a constant multiple there. 6 is multiplied by everything. So I'm just going to take that outside of the integration sign. I won't write it all out again. I'm just going to pop that 6 over here. All right, I'll multiply it in at the very end. Hopefully it's okay that I'm kind of skipping that step. So I have 6 times. Now, integrating cos squared of t. And this goes back to, remember I said I threw in some links on revision of integration of cos cubed, sine squared, etc. If you have an even powered trig part, well, cos and sine. So if you have an even powered, cos squared is an even power of cos. But likewise, if it was sine squared, we use the double angle identities. So in the tables, and this is just, I mean, students always ask, is it always this way? Yes, it's always this way for even powers. In the tables, you'll see a formula in the trigonometry page for cos. That's a formula from the trig tables. If you have cos raised to a square or sine raised to a square, the sine squared one is a half of 1 minus cos of 2x. But you'll see those in the tables. Here we just have cos squared, so I'm using this. We always rewrite these in terms of that when we're integrating them. So I'm not integrating it yet. I'm just changing how that cos squared term looks. So it'll be 36 times, instead of cos squared of t, I'm going to say it's a half of 1 plus cos of 2t. So instead of x in the tables, I have t. So it'll be a 36 times that. I'm just leaving the other terms for now. Simplify things down if I can. So 36 times a half is 18. 18 times 1 plus cos of 2t plus 12 sine of t. Sorry about this, folks. 12 sine of t plus 1. And I can multiply in the 18 as well. So I haven't done any integration yet. I'm just basically changing how it looks for the purpose of integration. So 18 times 1 is 18. 18 times cos of 2t is 18 cos of 2t. I have 12 sine of t. And I have a plus 1 at the end. Now, 18 and 1 is 19. So again, I'm just going to write 19 there and get rid of the 18. Again, hopefully that'll be clear afterwards when you look through them. Now, remember, don't see that formula. Sorry. I turned on notifications when the chat will come in, but they must be after turning off. I don't see that formula. The one I see is a half x. I think it's on the, if you go to the second trigonometry, let me think, I don't have a copy of the tables. If it's on page 15, 14 or something. Yeah, I think it's the second page, Genevieve. It's the second page of the trig. So on the first trig page, you have that table with pi over whatever, and it gives you all the different cos and sine values for it. I think it's on the next page in that. I think. Somebody does have the tables. It's on page 14, is it? So Genevieve, if you just have a look at page 14, people are saying it's there. Sorry, I don't have tables on me. Okay, lovely job. So we're going to integrate it now. Now, do you remember I was saying about the differentiation of cos of, if I was differentiating cos of 2t, cos will go to minus sine of 2t, and then I would multiply by the derivative of 2t. With integration, it's the other way around. So as long as it's not cos squared or anything, cos squared we changed, but the cos of 2t, cos integrates to sine, So it will integrate to sine of 2t divided by 2. That will be the integral of that. So I'm going to integrate now. And is not good today. So it'll be 18 times cos integrates to sine, but it will be divided by 2. Sine integrates to minus cos. It's just sine of 1t, so I'll just read it straight from the tables. That'll be minus 12, the cos of t. And a constant with respect to t will just give me the constant times t. And I have limits of pi over 3 and minus pi over 2. I'll tidy this up very slightly. 2 into 18 goes 9 times. And I'll multiply into 6, and then I'll substitute in the limits. So 6 times 9 sine of 2t is 54 sine of 2t. I have 6 by minus 12 is minus 72 cos of t. And I have 6 times 19 t, so 6 times this one is 114 t. And that's between, again, our limits now that we can sub in are pi over 3 and minus pi over 2. So just because they have pi's in them and all that kind of thing, it's still the same process. We sub in upper limit minus lower limit. So my upper limit, sine of 2 times pi over 3 minus 72 times the cos of pi over 3 itself. I'm just replacing all the t's with pi over 3 for the upper limit. That's our upper limit gone in, minus sub in our lower limit. So 54 sine of 2 times minus pi over 2 minus 72 times the cos of minus pi over 2. Make sure to be putting those in brackets when you're subbing them into a calculator. And plus 114 times minus pi over 2. And if you work all that out, like make sure your calculator's in radians first and foremost, and then substitute all in all those values, you get approximately 309.22. So that's our line integral for C2. So we've done it along C1, the line segment, and we've done it along C2, the circle. So our overall answer, therefore the overall C that we were asked for in the question, is just our answer from along C1, which was minus 23.77. Sorry about this, folks. Replace the nib. 309.22. We add the one along C2, and you're getting an approximate answer for that. 285 point something. And I'll just do it out. Minus 23.77 plus 309.22. 285.45. That would be the overall answer. But you parameterize them both separately, work out each of them individually, then add the two answers together. That would have been that question 3. Bit more complicated just because of that circle, I think. And as well, just do revise the likes of integrating these. I've put the 2 links in the slides to 2 revision videos on them. I think in those videos, it does a product of cos squared times sine squared. And I say, oh, use this one and use the sine squared one. But even individually, if it's just cos squared, you also use this. So I think the recording I did was when they're multiplied together, cos squared of x times sine squared of x, integrating that. But even when they're just on their own, you use those identities as well. So maybe the ones in the videos are a bit more complicated than separately, but even separately, you still use those identities. Okay, so that's question 3. Questions or anything on it, or? Okay, look at question, what say we do next? Question 5. So question 5 said, consider the region. You weren't given this thing. I'm putting in screenshots of the graph as it goes along. Consider the region in the XY plane bounded by x equals to y squared, x equals to 4, and y is equals to 1. And we're asked to sketch this region in the first part of the question. So I'll put in the graph bit by bit. I'll start with x is equals to 4. X is equals to 4 is just a vertical line at x equals to 4. Why? Because along any point on that line, like here's the point 4, 1, here's the point 4, 2, here's the point 4, 0, here's the point 4 minus a half, i.e. x is always 4 along that line. That's why it's just a vertical line, because the x value of the coordinate is always 4 at x equals 4. Likewise, y is equals to 1 would be a horizontal line at y is equals to 1. Because if I picked any point along that, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, y is always 1. So there are two x equals to 4 and y is equals to 1. The last one is x equals to y squared. Now, x equals to y squared, I mean, y equals to x squared is just your normal quadratic U shape touching at 0, 0. So that's just that rotated. If you're not too sure about sketching it, do out some points. So when y is 0, and y is equals to 0, x will equal 0 squared. So x also equals 0. So 0, 0 is a point on this curve. When y is 1, x will equal 1 squared, which is 1 squared. So 1, 1 is on it. There. At y is equals to 2, x would equal 2 squared, which is 4. So when x would equal 4 when y is 2. Look, I'll just keep writing them for the sake of it. When y is equals to 2, x would equal 2 squared, because x equals y squared is what we're told. At y is equals to minus 1, x would equal minus 1 to be squared, which is plus 1. So x is 1 when y is minus 1. So 1 minus 1 is on it. And we do one more at y is equals to minus 2. X equals minus 2 to be squared, which is plus 4. So x is 4 when y is minus 2. So again, 4 minus 2 would be a point as well. And you would just draw your curve through all those points. So sketch the region. Now the region is, we're told, consider the region in the xy plane bounded by x equals to y squared. So we have our 3 curves in. The region bounded by all of those is that region there. That's the one that's enclosed by all 3 of the curves. All right. So that's R. That's our region R. All right. So that's our region. Now we're going to go away and try and work out part B. So it says, write down the repeated integral that represents the area of the region. Now, area is a double integral on the region of 1 dA. Area is 1 times dA. It's different to where you'd have a scalar field in there, if you'd x plus y or whatever. Area is 1. And we can write that a bit differently. dA, I said to you yesterday, dA is dx dy. Remember, we had dA equals dx dy, and dx dy equals r dr d theta would be the polar version of it. But if I'm integrating with respect to x, I need x equals on the first two limits. If I'm integrating with respect to y second, my second integral should be y equals something, right? So I'm going to go in now and try and find what those limits are. So for x, well, the x one, it goes up as far as 4. That would be my highest x value. And all the other x values are determined by x equals y squared. So it's in this region. It goes up as far as x equals to 4. And all the other values before that are determined by x equals y squared. So my area equal, leave the outer integral a second, that x equals to y squared. You could also do this the other way around, but I'm just doing it this way. You could do it dy dx and do it that way as well, but this is just easier in this particular question. So x will equal y squared, and it will go up as far as 4. The y values then, so I need y equals, well, y will go from 1 in this region, y will go from 1 up to 2. They will be the y values in this region from 1 to 2. So they would be our limits for our integration. Now, if you're not certain about the y ones, maybe the x ones are okay from the sketch, but about the y ones, well, y is equals to 1 is kind of a clear enough one, I think, when you have the sketch done and you've the region identified. But the upper one, so it has to be where x equals to 4. It has to match up with that. So 4, when x is 4 equals y squared. So y will be the square root of 4, plus or minus. So plus or minus 2, but quite clearly it has to be plus 2. We just solve that. So that will give me the upper y. So that's our area integral, which is part B. That's part B done. And then it says evaluate that. So we're going to go ahead and integrate that. Y is from 1 to 2. X is from y squared to 4. And our area is 1 dx dy. The x. Right? So let's go ahead and start integrating. I do my inner integral first. Yeah, we work from in to out. So integrate 1 with respect to x. Well, integrate 5 with respect to x, you get 5x. Integrate 1 with respect to x, we get 1x. Leave the outer integral. So integrate 1 with respect to x, I just get x. And I have limits on that of x equals y squared and x equals 4. And my dy term still left on the outside. So I still need to integrate with respect to y. But I'll sub in my limits. So sub in my upper limit, which is 4, and it's going in for x, minus sub in my lower limit, which is y squared. So upper limit minus lower limit. So there are those two limits substituted in. Now I'm going to integrate with respect to y. So integrate 4 with respect to y, I just get 4y. Integrate y squared with respect to y, add 1 to the power, divide by the new power. And I have y limits of 2 and 1. So again, substitute in upper limit minus lower limit. 4 times the upper limit is 2. Upper limit minus sub in the lower limit. The area in question would be 5/3. If you calculate all that out, you'll get 5/3. As I said, you could have also taken the area integral the other way around. You could have said it's the double integral of 1 dy dx, and you would have had set up. So I'll just talk through it just for the sake of it, right? You could have, or you could have gone the double integral. Leave a bit more room there. Of 1 dy dx. If I'm integrating with respect to y, I want y is equals to. Then I'm integrating with respect to x, so I want x is equals to. So if I was to do it that way, y, look, y would have gone from 1 up to x equals to y squared. Solving that the other way around, if y squared is x, y is equals to root x. So y would have gone from 1, and any other value above that would have been root x. So y is equals to root x. And the x values then would have been from 1 to 4 in this region. So the x values would have been from 1 as far as 4 for that region. So that's another way you could have done it. Integrate with respect to y first, then integrate with respect to x. I'm very sorry about the pen. It's not working out very well today. But that's question 5. But area is just, area of a two-dimensional thing like that, it's just 1 times dA. It's the double integral of 1 dA, and then dA is either dy dx or dx dy. You can take it whichever way you want. Doesn't make a difference, you'll still get the same answer. Okay, so that was question 5. Question 6. Now, I want to just pull in, try to do a little mock-up on GeoGebra, but let's read it first, because I think this one caused some trouble yesterday, my own doing. It says, write down the triple integral using Cartesian coordinates. Cartesian is x, y, z. That would be used to evaluate that triple integral there, where E is the region bounded by the cone. So we're given a cone, z equals the square root of x squared plus y squared, and the plane z equals to 2. So just briefly, if I can pull this across. Right, so here is, by the way, this is, if you go into on our Solar site, if you do want to sketch anything like this on your drop-down 24/7 drop-down thing, I've had like useful tools that you might find helpful, or I've called it something like that. This is just a 3D calculator on GeoGebra. So I've put in the cone, which you can see there in blue. So it's just a cone centered at 0, 0, 0. So when x is 0 and y is 0, z is definitely 0. So 0 is definitely a point on that cone. And it has the z-axis as the vertical kind of axis of it. And the plane z equals to 2. So z equals to 2. I'll just pull this down. I'll just zoom in a bit. Like, here's the z value of 2. Hopefully you can see that. So a plane z equals to 2, just flatten out the x and y plane, is if I take, let's say, a flat sheet of paper at z is equals to 2. If I rotate it back around, you'll see the plane is that red portion, right? That red plane there. So I'm asked to evaluate E is the region bounded by the cone, and this plane z is equals to 2. So the cone comes up and its z is equals to 2. Now, we'll talk through, I might come back to this again in a sec, to this thing here when I'm talking about the projection side of it. But let's deal with the height element of it first. We'll take the height out of it. So just pull this back across a sec. Okay. So to get rid of that height element of it, we did the same thing kind of yesterday. So we have our triple integral. E is the region, the full region itself, bounded by the cone and the plane z is equals to 2. But if I want to take the height element out of it, that would be the z element. I'm going to rewrite that as region R And dv, I'll come back to r there now in a sec. I'm going to deal with the height. And when I have the height dealt with, what we'll be left with underneath then is area. So I need z limits. Z goes up as far as 2. That's the red plane was z is equals to 2. All the other values underneath that are determined by that. So z is equals to the square root of x squared plus y squared. That would be the initial setup. Deal with the height element of it first. Now I'm going to split area into x's and y's. And I kind of mentioned yesterday about projections and projecting it down. So if I pull this thing back across, hopefully it'll be visible. Okay, I think it is. So when we're talking about projecting it down, so I have the height element dealt with in the z limits and the dz term, but now I'm dealing with the a, which is the area term. So if I just have a look down on it, what I'm talking about now that's left over is that circle. So that circle is built from where the plane intersects with the cone and projecting it downwards. So imagining that that circle is being pushed down onto the x, y plane, right? So the equation of that circle, it has radius 2 and it's centered at 0, 0. So it'll be x squared plus y squared equals radius squared. So x squared plus y squared equals 2 squared. So x squared plus y squared equals 4. Now, again, if you're not fully sure on that, like, so let me just. I have my z's. And let's say I'm going to split dA into dy dx. Doesn't really matter. dx dy or dy dx. But if you're not too sure about the circle, right? The circle is built from, where did that thing go again? The circle is built from intersecting the plane z is equals to 2 with the cone. It's the intersection of those two surfaces that builds this circle, right? So, well, to intersect two things in maths, you let them equal to each other, because it's literally where does the plane equal the cone, right? So if you're not too sure about the equation of this circle, well, it's where the plane equals the cone. So it's where 2 equals the cone. And if you square both sides of that, 2 squared is 4. Square a square root sign, it just cancels with the square root sign. So that will be the equation of that circle. If you didn't have, let's say, the graph, which maybe you wouldn't. But that would be the equation of the circle. So if I'm integrating now, let me do 2 secs. On a scale of A to D, A being, yeah, I can visualize that, to D being, I haven't a clue what's going on there. How are we kind of so far on the visualization? Just visualizing the idea. Okay, so let's talk through it once more. So when we have this set up, right, as I said, the cone, whoops, it is. The cone is just that cone. So ignore the top of it, it's just being cut off by the graphics. But the cone is just that cone center that has 0, 0, 0 as a point, because when x is 0 and y is 0, z will equal 0. It will equal the square root of 0 squared plus 0 squared, which is 0. So 0, 0, 0 is a point on this cone. And everything else has to be positive, because when I square x and I square y, regardless of what they are, it'll give me a positive number. It has to go upwards into the positive z-axis. So that's our cone, and it's bounded by the cone and the plane z is equals to 2. So that's like I laid down a flat sheet of paper. Whoa. a flat sheet of paper at z is equals to 2, and it's going to intersect with that cone. So the region I'm talking about is the cone. So the region E is the cone from 0, 0 up as far as that bit there. So when setting up the triple integral, the first element that we deal with is the height side of it. So what's the story with all the height values there? Z is going up as far as 2, and any Z value underneath that is given by Z equals the square root of x squared plus y squared. So in my triple integral, instead of saying it's the region E, which is the full three-dimensional thing from 0 up to Z is equals to 2, the cone from 0 up to as far as Z is equals to 2, and talking about it in terms of V, in terms of a volume term, I'm going to take out the height element of it, Z, the Z element of it, and say, well, Z goes up as far as 2 on that cone, and any Z value underneath that is given by this. So that's the height element taken out of it. Once we've dealt with the height element, well, we don't need to worry about height anymore. So if you picture, say, let's say a cube, if you look down on a cube, if you project the cube downwards onto a flat surface, it's a square. Here, when the height element is taken out of it, and I just look down on it, I project that intersection thing down. I'm just talking about area. So if I grab that intersection of the cone and the plane and project it downwards, I just look down on it basically and imagine that it's sitting on the XY plane, I'm talking about area. And it's just a circle where they would intersect. I mean, if you have a perfectly upright cone and you laid a flat piece of paper through it or cut it with a flat piece of paper, it would give you a circle. And that circle has a radius of 2. So x squared plus y squared equals to 2 squared. X squared plus y squared equals to 4. But mathematically, we can find that by just intersecting the plane z is equals to 2 with the z of square root x squared plus y squared. So just let 2 equals to the square root of x squared plus y squared, and that will be the equation of your circle. So area, dA is the same as dy dx or dx dy, whichever. So I am now going to, well, I have my z limits, right? The radius of the circle is 2. Yeah, so, well, like, as I said, you might have access to this thing here. Like, that the radius of that circle goes from 0 out to 2 and back as far as -2. But more mathematically, what you'll be doing is you'll be setting, so the plane z equals to 2 intersects with the cone this when z is 2. So fill 2 in there for z. So 2 equals the square root of x squared plus y squared, and then just square both sides because it should be a circle. All right, so you just let z is equals to 2 in both. You kind of like you're doing simultaneous equations in a way. But we have our z, so we have our height things. Lovely job, they're taken care of. I need now y limits, so y equals. Well, if this is my circle, remember now I'm just talking about the projection, I'm just looking down on the circle. So y will equal 4 minus x squared. I'll say y squared, look, it's 4 minus x squared. So y itself, I need an upper and a lower limit. So I'll say plus or minus the square root of 4 minus x squared will give me my y limits. So y will be from minus the square root of 4 minus x squared up as far as plus the square root of 4 minus x squared. Finally, our x limits then, it's our last integral, and they would be extreme values. So they would be numbers. So x will go from, if you imagine looking down, I mean, it's a circle centered at 0, 0 with a radius of 2. So x will go from -2 to +2. So that would be the Cartesian coordinates. That would be the full integral written out in terms of Cartesian coordinates. All right. Now, if you're given the diagram, I think it helps. You're kind of weren't given it. You could do a mock-up of it. In the solutions, there's a quick mock-up done, and you can see if you do have the solution file, there's like these vertical dotted lines dropped down onto the XY plane. That's the projection that I'm talking about. Imagining that intersection of the cone and Z is equals to 2 just popped down onto the XY plane, that circle. So that would be the triple integral written out in terms of Cartesian coordinates. Then part B asks, I'll probably write all that stuff out again. I left way too much space before part B, did I? Well, part B says use an appropriate change of, sorry, it's written right there. Use an appropriate change of variables, evaluate your integral from part A. So we're going to use cylindrical coordinates because there's an x squared plus y squared in it. An x squared plus y squared in cylindrical coordinates is r squared. And that was given in the formula sheet in the 2022 paper. So I'm going to rewrite that triple integral in Cartesian. And Z from root. X squared plus y squared dz dy dx. So in cylindrical coordinates, we have x squared plus y squared is r squared. Right, that's one of your terms that you're given in the formula sheet for it. So I'm going to start replacing. Now, what I did say to you yesterday that I'd just recommend memorizing, to be honest, is dA is dx dy or dy dx, whichever. In cylindrical, it's r dr d theta. Right, so that's how you're going to transform this from dy dx or dx dy, if you go about it that way, to cylindrical. So dy dx will be replaced by r dr d theta. X squared plus y squared, in the formula sheet it's given, that's r squared. The square root of x squared plus y squared. So, well, if x squared plus y squared is r squared, we square root both sides. Square root of x squared plus y squared is the square root of r squared. The square root of r squared is just r. So r will just be going in instead of the square root of x squared plus y squared. Right? What else do we need to replace? Well, following that, then we won't have y's and x's anymore. We're going to have drs and d thetas. So we're going to deal with that. We'll deal with that afterwards. Let's just start replacing what we can. By three integrals. Z will remain, as you'll see in the cylindrical coordinates formula sheet, z equals z. So z stays the same, right? So z will equal, instead of the square root of x squared plus y squared, we're now going to replace z with just r down there. And it goes up as far as z is equals to 2. Because if I'm changing to cylindrical coordinates, I don't want x's and y's in it anymore. So if z is equals to the square root of x squared plus y squared, I have to change that square root of x squared plus y squared into something else, into something that deals with r, because I'm changing the coordinate system. X squared plus y squared, straight out of the tables, is r squared. dz, as I said, z staying the same. dy dx is r dr d theta. And we can tidy that up in another bit. Just by combining r squared multiplied by r is r cubed. I'm just going to do that first. Cubed. z, and I still have dr and d theta there. So I need to create limits now for r and theta. So I want r equals and theta equals. In that circle, remember the projection down, the radius of the circle was 2. So the distance from the origin to any point on that circle is between 0 and 2. So my r limits are from 0 up as far as 2. They would be the r limits. Because again, if you just pop that up visually a second. So when I project this shape down, the distance from the origin to any point along that surface, point could be here, that distance from the origin, up as far as 2. So we'll start at, literally, it could be at the point, so the distance would be 0, up as far as 2. Our theta limits then, well, it's a circle, so I go from 0 to 2 pi. They would be our theta limits, from 0 to 2 pi. So there is our change of coordinates, and now we're going to integrate that. R was between 0 and 2. And we'll integrate r cubed with respect to z first. So our first integral is with respect to z. So I'm going to treat r as a constant. So integrate 5 with respect to z, you get 5z. Integrate r cubed with respect to z, you get r cubed z. And I have limits of z equals r up as far as z equals 2. And I still have dr d theta at the end. So I've done my z integral. I've integrated with respect to z. So I still have dr d theta at the end. And I'll plug in my limits. They're going in instead of z. Said to you yesterday, I always write down z equals so I know what those are going in for. Sometimes it can get a bit confusing if you don't write that. So r cubed times the upper limit is z is 2. So r cubed times 2 is 2r cubed. Minus, sub in the lower limit for z, which is r. So I'll have r cubed times r, which is r to the power of 4. So that's our z integral and the limits in for that. Next, I'm going to integrate with respect to r. Well, both of those terms just have r in them, so I'm just going to carry out my normal integration on them. So I add 1 to the power and divide by the new power. Add 1 to the power, divide by the new power. And I have limits on that of r is equals to 2 and r is equals to 0. Again, upper limit minus lower limit. So d theta is still just there at the end. I sub in my upper, when I sub in the lower limit, look, it'll just give 2 times 0 to the 4 minus 0 to the 5. So the lower limit will just go to 0. So I'm not going to sub that in. If I sub in the upper limit, I get 2 times 2 to the power of 4 is 32 over 4. 32 over 4. Minus, sub in there, we get 32 over 5. 32. That would be the upper limit. As I say, minus 0 as the lower limit. When we sub in the lower limit, we'd get 0 out of that. All right. So we now just have to integrate with respect to theta. Well, 32 over 4 minus 32 over 5. Is 8 over 5. Might as well do that. If I made an arithmetical error with that, let me know. That's 8 over 5. D theta. So I'm now going to integrate with respect to theta. So integrate any constant with respect to x, you'd get the constant times x. Integrate a constant with respect to theta, I'm going to get that constant times theta. And I have theta limits of 2 pi and 0. Then if I substitute in 0, 8 over 5 times 0 is 0, so I'm not going to bother subbing that in. But I'm subbing in my upper limit, 8 over 5 times 2 pi is 16 pi over 5. That would be your value there. You can approximate that on a calculator if you want. You can type it in and see what approximately it is, but there's no need. So that would be the question 6 from that paper. All right, that's it. Unless you've other questions you'd like to ask, that's it really. But
Richard,
I'm happy to.
Sorry, quick question. On that 6 that you did, it says write down the triple using Cartesian. Why did you convert it to cylindrical, or did you just want to show us how to do it?
No, so part A said write down the triple integral using Cartesian, right? Cartesian is x, y, z's. X, y's, and z's are Cartesian, right? Then in part, so that's why I did this. This was the answer to part A, right? In part B, it says using an appropriate change of variables. So the appropriate change of variables in part B is to change it to cylindrical because of the x squared plus y squared in it. So the answer, part B starts here.
Okay, super, so thank you.
The change of variables is from Cartesian. I'm changing it from Cartesian variables to cylindrical variables.
Okay.
All right.
Thank you.
All right.
Richard, can I just ask you, you know where you subbed in the Z limits?
Here?
Yeah, why did it become 2r cubed? Sorry, no, I'm brain is fried.
That's okay. So, no, you're great. So, when we integrated it, integrating r cubed with respect to z, I'm treating r cubed like a constant, so I'll just get the constant times z. So r cubed times z, right? So r cubed times z, and I do have z limits of 2 and r. So when I would go subbing them in, sorry, this pen is.
Oh yes, it's 2r cubed. Yeah, is for the first limit,
It'll
and
be
then r is just
exactly.
The second limit. Yeah. Sorry,
exactly. So the second limit will be r cubed times r, which gives the r. That's all right. No worries. No worries. No problem. Look at question 4. Question 4. Finding the start and end points. Question 4. Seconds. I don't have question 4 in the slides now, but is the work done? Is this Miriam? That. Yeah. Okay. So look at question 4, and I assume it's the t values, Miriam. Is it that you're not too sure about? Yeah. All right. So question 4, I don't have it on the slides, so you have to open the actual paper, right? Hopefully the pen will hold up. Right, so it says find the work done by the force field. So we're given a force field, F. I'll just write it down just in case it's needed. We have a good bit of time, so not too bad. 2yz squared j plus x. So that's our vector field, which is a force in this case. In moving a particle from, I was spelled from incorrectly. I was right form. Very annoying. 2 minus 1. 2, 11, 8. 11, 8 along the curve C. The curve C, and the curve C is given by y equals 3x squared minus 1, where z is equals to x cubed. Okay, so work, first and foremost, anyway. the line integral on the curve of f dot dr. So that's your formula for curve, or for work, sorry. It'd be the dot product of f and dr. So we are going to parameterize that curve. So from -1 to -1 to 2, 11, 8. So, I mean, R in general will be X, Y, Z. So R in terms of T, like our X will be X, our Y will be 3x squared minus 1 from above, and our Z will be X cubed. Whoopsie daisies. From above. That's just like I'm just assigning X to be X. Y will be determined by 3 times whatever the X value is to be squared minus 1. So if X is just X, Y will be that value, and Z will be X cubed. So if X is X, then Z will be X cubed. But in terms of T then, I'm just going to say that it's T, 3t squared minus 1, and T cubed. But we do need to find the T values that start and end it. So that's our R of T. But to find the T values that start and end it, like look at the starting point at the start. I'll just write -1, 2, -1. That's the start point. This value has to equal -1. So T has to equal -1 for the start. Or you could solve T cubed has to equal -1. So T again would be -1. Or if you let the middle one equal to 2, T would again, if you solve that, would come out to be -1. So T definitely starts at -1. And it's up as far as the end point is 2, 11, 2, 11, 8. So again, for this to actually match the end point, the T value has to equal 2. So it'll go from T being -1 up as far as 2. So they will be your T values for that. And then you go through the same thing as we went through in the other question. I think there was a similar one in 2011. So you parameterize it first, and then obviously you find the T values to start and end it, and go from there. No worries. How do we get an X? So, like this thing here, I assume what you're talking about. So, like Y equals something that deals with X's, right? I would have thought X was 3. Like this curve, right? We're told 2 seconds. So for this curve, we're told Y depends on X. Y equals to 3 times whatever X is to be squared minus 1. And for Z, X equals whatever X is to be cubed. So X is kind of like the basis, right? And then Y will be determined based on the value of X. So if X is 1, for example, Y will be 3 times 1 squared minus 1, and Z will be 1 cubed. If X is 2, Y will be 3 times 2 squared minus 1, Z is equals to 2 cubed. If X is 4, Y equals 3 times 4 squared minus 1, and Z is equals to 4 cubed. So X is kind of like the basis that we then generate Y and Z from. So if X is just X, for example, the Y value will be 3 times X squared minus 1, and the Z value will be X to be cubed. If X is T, for our parameterization, if X is T, the Y value will be 3 times whatever T is to be squared, and Z will be whatever T is to be cubed. So it's not that there's a specific value for X. It can take a range of values technically between -1 and 2. Did I say actually, sorry, I said at the start, didn't I? Did I go back and I do 1b? I think I'll do that. Some of it done, but actually nearly all of it done. You'd literally be just subbing in the values after that. So I did it at the start. A bit all over the place, but oops. Yeah, it was here. So our unit tangent vector is r dash t, which is this, over the magnitude of r dash t, which we worked down as far as here. You just pop that underneath, and then you'll be subbing in your values. You're asked for the unit tangent vector at a point, I think. At the point -1, 1, 2. So you'd sub in 1 for, well, no, you'd actually have to find the t value for that. Yeah, let's talk through 1b, because it is parameterized. And then again, this is 2022. Lost total track of these slides. Left too many blank slides in certain places. So 1b. It says to find the unit tangent vector. So our formula for that is there. But we're asking for the unit tangent vector. We're given r of t is t cubed. No harm in going through it again. R of t is t cubed e to the t squared minus 1, 3t plus 5. So our unit tangent vector at the point, write that down as well, -1, 1, 2. Okay. So for our formula for the unit tangent vector, we need r dash t, which kind of covered at the start. We just differentiate it, 3t squared. E, it's not just e to the 1t, it's e to a whole bunch of stuff. So from the tables, e doesn't change. E to the x goes to e to the x. But because it's not just because this is what's called a composition function, it's not just a single t in the power. We need to multiply by the derivative of that inner function there. Differentiate t squared minus 1, you get 2t. Differentiate 3t, you get 3. Differentiate 5, you get 0. So that's r dash t over the magnitude. So we also need to work out the magnitude of r dash t. So it'll be the square root of first term in r dash t to be squared plus the second term in r dash t to be squared plus the third term to be squared. Now we simplify each of them down, which we did already. It'll be 9t to the 4 plus 2t to be squared is 4t squared. Anything raised to a power, raised to another power, you multiply the two powers. So t squared times 2 is 2t squared. Minus 1 times 2 is minus 2. Plus 3 squared is 9. So in terms of t, our unit tangent vector is r dash t, this, over the magnitude, which we just worked out. Now, we're asked to evaluate that unit tangent vector at a point. So you see, like, the point is in Cartesian coordinates, x, y's, and z's. So we're going to have to find the t value that goes with that point, right? Because I can't sub in x, y's, and z's into what I just wrote. So let's see. Well, if this is the x of r of t, remember it goes x, y, z, that has to equal -1. T cubed has to equal -1 in the parameterization. So solve that for t. The cube root of -1 is -1. Or I'm definitely not going to take the middle one as a solution thing, too awkward. Or you could solve like 3t plus 5 would have to equal 2. That would also give you the t value. So 3t is 2 minus 5 is minus 3. So again, t would equal minus 1. As I said, you could solve the middle ones as well if you wanted. E to the t squared minus 1 equals 1, but too much work. So we're going to sub in minus 1 for t. That's the value, the t value that corresponds to this point. So I would evaluate that when t is minus 1. So just replace all the t's with minus 1 and work it out. All over the square root. Then replace all the t's with minus 1. And work each of those down. The calculator will deal with that anyway for you. Root of 9 and 4. 9 4 is 13, 9 is 22. 9 is 22. And then just to put them all over the same thing, like it's a unit vector we're looking for. Like usually a vector just, it doesn't have over magnitude or whatever, it's literally pointed brackets with the x, y, and z in them. So just to put each of those then, so it'll be 3 over root 22 will be the first component of the vector. 3 over root 22 minus 2 over root 22 over root 22. And the last one is 3 over root 22 again. That would be your unit tangent vector. You do a little check if you had a bit of time. If you work out the magnitude of this, as it's a unit tangent vector, a unit vector has a magnitude of 1. So if you worked out the magnitude of that vector at the very end, it should have a magnitude of 1. That would be the 1b. 1a is literally a definition. So know your definitions. But yeah, that's it. Happy to stay on for another 5 minutes or so, but other than that, very best of luck with it. I hope you get on well. Hopefully what we've covered here will come up and stuff for you.
Thanks very much, Richard. It's been really helpful.
No problem. No problem. You're welcome. No worries. No worries. No
Thanks, Richard. Thank you.
No bother, Helen. You're welcome. If there's anything else I can answer or whatever, feel free to ask.
Thanks. Thank you.
No problem. No problem. Good. Good. I'll put the slides up again anyway after this. No problem, folks. Best of luck with it. Look. Take care. Very best of luck.